This is a picture of an alternator. Basically, it's a spinning coil of wire in a magnetic field. They've drawn it here so that we can understand it. We'll look at how an actual alternator is designed. Okay. Remember that what Faraday's law states, at least in the IB version, it's minus n change in flux over time. Anytime you start seeing these little deltas like that, obviously there's it's calculus going on, right? It's really a derivative. Okay. And remember, flux is BA cos theta. Okay. Now, if this thing is rotating at some angular velocity, this is in radians per second, right? Okay. Then that angle changes, right? Because it's BA cos theta, right? Right. So a real simple model for theta is just that it's omega times t. It's rotating. It's constantly changing, right? So that's what's changing. If we take the derivative of that, we have to use the chain rule, and this is like one of the simplest things, right? B and A are constant, right? Okay, let's assume that, I don't know, whatever our windings are, right? We'll end up with minus NBA, those are our constants, right? And then the derivative of this is, let's see, cos, is that negative? I think so. Negative omega sine omega t, right? Okay, is that right? Let's see, cos. Cos does this, yeah, so the rate at which it changes is derivative of cos is negative sine. So it starts at 0 and then gets negative. Yeah, okay, good enough. I always have to remember that. Okay, dt, so this is our derivative, right? Notice that, the minus signs, maybe I've dropped a minus sign or something anyway, but notice that you end up with omega times NBA sine omega t. Right? And so this thing ultimately is sinusoidal, right? The output is sinusoidal, and this amplitude there is NBA times omega, right? So the faster you spin it, the higher this is, right? The bigger that area is, the stronger the magnetic field, the more windings you have. All of those create a higher EMF, okay? And yeah. Yeah, there we go. And then the second thing to keep in mind is that as you draw current from this thing, okay, that current flows in such a way to oppose that rotation, okay? The current that's flowing in there is opposing this rotation. So the more current you draw, the harder it is to turn this generator, okay? It can't make it easier, right? Because then it would be acting like a motor. We'd violate conservation of energy. It must be that the work you're doing is manifested as electrical energy, right? So if you demand more electrical energy, you must have to do more mechanical work, right? Okay. Let's just look at an actual alternator. So this is the thing that creates the north and south poles, right? So inside there, it's not enough to just have a magnet, a permanent magnet, right? We've got an electromagnet, so we have a super strong north and south pole. And then does this look like there's lots of little loops of wire there, right? Not just one loop, but lots of loops, right? Cleverly connected, right? Okay. And then these are actual little pieces of ferrous material iron, right? That intensify that. Okay. And so, yeah, I had an old alternator as a kid, and I wanted to get the wire out of it. Well, good luck getting the wire out of this thing, right? I was so sad. All that good wire, I couldn't get any of it. I was a wire-seeking child, right? Okay. And I've got a demonstration here where you can actually light up a light bulb, and you can see that the more load you put on it, the harder you have to turn the crank of this alternator to do that. This is, of course, how Priuses and Leafs and electric cars with electric motors slow down, is that they turn their motors into generators. There's very little difference between a motor with fixed magnets can easily be a generator. Okay, and so the Priuses and Leafs and things like that use the forward motion of the car to actually generate electricity as they slow down, and they store that energy in their batteries. They don't get all of it, but they don't lose all of it either. Okay. Anyway, demos in class.